Right here with the notes for section 10.2, statistics and graphical representations. So we got some definitions. So the objects described by a set of data are the individuals. This could be people, animals, or things. The characteristics of the individuals being studied or measured is the variable. So the height of people, the weight of a car, things like that. If you use data to identify each individual as belonging to a distinct class, such as male or female, that's referred to as a categorical variable. So the category they fall into: two-door car, three-door car, two-door car, four-door car, SUV, minivan, sports car, coupe, things like that. If we use the data as numerical values, measuring the characteristic, that's a quantitative variable. So they're sorted by their numerical value. So numerical values are summaries, sometimes are called statistics, describe the properties of the data, such as counts, percentages, or averages. So categorical data. Categorical data is often displayed graphically, as in a bar chart or a pie chart, sometimes called the circle graph. So your categories are here across the bottom, or the labels for the wedges, and then you have your values here. So number of deaths. Over here you have percentages from the whole, things like that. But one variable is a word, a category. The other variable is the number. All right, so quantitative data, a quick way to organize and display a small set of quantities with a stem plot, also sometimes called the stem and leaf plot. Each number in the data set is split into a stem, consisting of its initial digit or digits, and a leaf, which is its final digit. So example 1. In the table below, it gives percentage of each state's population that was 65 or older. Make a stem plot for the data. So what we're going to do is, let's see here. So you would have to label our stem, and then we'll have our leaf. So our stem, let's see here, we'll call the stem the ones place. So it looks like the smallest value here is Alaska at 7. So 7, 8, 9, 10, 11, 12, and I think the biggest one, 13, 14, 15, 16, 17. So there's our stems. And then the leaves are going to be the tens place. So for example, for Alaska here at 7.7, its leaf would be 7. Now, there is no states that have 8. There is a 9.0, 10, there's a 10.3, 7, and 9. 11 has a 4. 12 has a, let's see here, a 0, a 2, a 3, a 3, a 3, a 4, a 4, a 5, an 8, a 9, and a 9. 13 has a 0, 1, 2, 2, 3, 4, 5, 5, 5, 5, 5, 7, 8, 8, 8, 8, 9. 14 has 0, 1, 2, 3, 3, 4, 4, 4, 5, 6, 8, 9. 15 has just 15.4 and 15.9. 16 has 0, and 17 has 3. So that's the stem plot. So you can tell most of the states here fall 13 point some odd %. And as you move away from 13, you get fewer and fewer. So that's a stem plot. Now, what you decide to make your stem can be different. So example 2, the per capita federal aid to state and local governments in the top 20 states is shown in the table below. Make a stem plot that provides a greater representation. What is the average of the 20 numbers? Why is the stem plot a better summary than the average? So let's see here. How do we want to organize this? We're going to round everything to the hundreds place. So $100 units. So let's see here. 1, let's see here. Actually, we're going to kind of do this. We're going to make 2 stems for each number, just to kind of spread the data out so you don't get big lists. So this will be the first like 0, 1, and then 0 through 5, and this will be 6 through 9. So 8 and 9. So that's like the 1800 and 1900. Here, 2, we got 1, 2, 3, 4, 5, 6. A couple 2200s, one 2300, and one 2400. So these are all 2000s. And then we have some 25s and a 2600. Let's see here. So there's our 2600, for example. For 3, so we have 3100, and that's it until we hit 3900, and then 4000. So there's your stem plot. If you find the average, I'm actually not going to show the work, but the average is you add them all up, divide by, in this case, what, 20? You get 2460. So 2460 is, would be essentially here. So the average is skewed by how many numbers are down here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and only 1, 2, 3, 4, 5, 6, 7 above. So the average doesn't lie actually right in the middle. Okay, so sometimes it's easier to compare sets of data if you have a visualization that allows us to view both stem plots simultaneously. That's done with a back-to-back stem plot. They use the same stems, but you have one set of leaves going to the right, one set going to the left, or vice versa. So example 3, Babe Ruth and Barry Bonds are two of the great sluggers in the history of baseball. Babe Ruth held records for hitting 60 home runs in one season and 714 for his career. During the 2001 season, Bonds hit 73, and he retired in 07 with a career total of 762. Who was the better home run hitter? The table below shows the number of homers hit each during his productive seasons. So, 0, 1, 2, 3, 4, 5, 6, 7. So our stems, we'll call their stems are going to be the tens place. So Babe Ruth has, let's see, 0, 1, 3, 3, and 6. So those are all the ones less than 10. For the 10s, he had one season of 11. For the 20s, there was a 22, a 25, a 29. For 30s, there was a 34 and a 35. For 40s, there was a 41, another 41, 3 46s, a 47, and a 49. For the 50s, there were 2 54s and a 59, and he had one season of 60. For Bonds, he had one season of just 5 home runs. Then there was a 16 and a 19, 24, 25, 2 seasons of 25, 26 to 28, 33, 33, 34, 34, 37, 37, 40, 42, 45, 45, 46, 46, whip off the screen, 49, and then one season way up here at 73. So there's your back-to-back. So, I don't know, what do you say? Babe Ruth is better? Yeah, this more seasons up here at 49, but, the majority of them are way down here. So that's just, a way to compare them. Okay, you can also have what's referred to as a frequency table. So the number of leaves for a particular stem is the frequency of that stem. Frequencies are often recorded in a frequency table. So here's a frequency table for Babe Ruth's home runs total. So 0 to 9 home runs, there were 5 years or 5 seasons he did that. From 10 to 19, there was just 1. 20, 29, 3, so on and so forth. So for a total of 22 seasons we calculated. All right, so histogram is related to a stem plot, displays the information in a frequency table. Visually, histogram is to quantitative data what the bar chart is to categorical data. Unlike the bar chart, though, axes in the histogram have numerical scales. The bars cannot be rearranged because you're counting. You can't move 2-door cars in front of 3-door cars to change the order of the categories. Bars on adjacent intervals have no intentional gap. So in a bar graph, when you draw your bars, you leave spaces in between them. In a histogram, you do not have spaces. The bars are directly next to each other. Leaving a gap means that whatever this interval is, has 0 items in it. So if we look back at the home run data for bonds between 50 and 59 and 60 and 69 would be 0 because there are no home runs there. This would be 1 unit tall, 2 units tall, so on and so forth. So if you look at, there's the 1, 2, 3, 4, 5 seasons, bonds hit between, or Babe Ruth hit between 0 and 9. All right, so make a histogram using the run totals in example 3, using an interval width of 10. So that's essentially this frequency table. So let's see here. We've got, what do you want to do? 1, 2, 3, 4, 5, 6, 7. So then this would be across the bottom. This would be 0 to 9. So 0. This would be 10, 20, 30, 40, 50, 60. Oops, 70. So between 1, 2, 3, 4, 5. So this one would come over height of 5. This one would have a height of 1. Between 20 and 30, be a height of 3. Between 30 and 40, height of 2. And you just keep repeating this process. Between 40 and 50, our height is 7. So if we come down here, between 50 and 60, we go to 3. 1, 2, 3's up here. And between 60 and 70, just 1. So there would be your histogram. Notice no spaces in between. Okay, shapes. You can also describe frequency distributions or histograms based off their shape. 2 aspects of the shape: modes and symmetry. A mode is an interval where the data tend to cluster and show up as longer leaf rows on a stem plot. So here you have these 2 shapes. This shape on the left is referred to as unimodal, has 1 peak. This shape over here is bimodal, bi meaning 2, has 2 peaks. Usually if this happens, you have 2 different groups being combined into the same graph. So like average heights of men and women, like you'd probably see kind of a spike like this because women in general tend to be shorter than men. Also, you have symmetry. This graph is symmetrical because if I draw my line through the tallest peak, it looks mostly the same to the left and to the right. You can't do that here because you have multiple peaks. The other thing you talk about is the skewedness. So the distribution in A here is referred to as skewed right because the tail runs to the right. This one is skewed left, tail to the left, which is, to me, counterintuitive. I would have called this skewed left. Most of the data is to the left, but the skewedness refers to the tail. Where is the tail occurring? All right. You could also do time plots, which are kind of like scatter plots, but same thing. So the Great Recession led many Americans to make change in their spending habits. The table below shows their total credit card debt leading up to and following the recession, display the data in time plot, and analyze the 9-year trend. So, so going across the bottom here, I don't know, do 04, 05, 06, 07, 08, 09, 10, 11, 12. Oh, I don't know. 1, 2, 3, 4, 5, 6, 7. Count by hundreds. So a little bit more. 07. Whoops. That's 39. So starts to come back down. 09 is 86. So, kind of a pattern like that. So that's just a time plot. It's a scatter plot where your x-axis is time units. So here you have the student loan debt. So plot it on the same axes. So we'll just come back up here. So in 2004, it was 346. So that's going to be about here. Then 392, we'll call it about here. Then 477, be about here. 538, 1, 2, 3, 4, 5. So you can kind of see the pattern, how it goes up like that. So that's what a time plot is. It's a scatter plot with time units. And that is the end of the section.